All right, ready to dive deep into pattern recognition and machine learning?
Always ready for a good deep dive.
Yeah, so you wanted to unpack this book, Fundamentals of Pattern Recognition and Machine Learning. Seems like it could be a bit dense.
Oh, it definitely gets into the nitty-gritty, but that's what we're here for, right? To break it down, make it make sense.
Exactly. And the author, Braga-Neto, seems to really get that balance between theory and practice, especially with all those examples from bioinformatics and materials informatics.
Yeah, those are great for seeing how this stuff actually plays out in the real world.
Okay, Chapter 1, Supervised Learning. This is where I always feel like I'm getting thrown in the deep end. Like, we have this magic box that's supposed to predict stuff, but how does it actually learn?
Good question. It's kind of like teaching a dog a new trick. You give the dog some input, a command or a gesture, and then you show it what you want it to do, like sit down.
So the dog is kind of like our algorithm.
Exactly. And the more you repeat it, the more feedback you give, the dog learns to connect that input with the outcome. Supervised learning is similar. We feed the algorithm labeled data, so each piece of data comes with the right answer already attached, and the algorithm figures out the relationship between the input and the output.
So the labeled data is like the training treats for the algorithm. So then what's prediction error? Is that like how often the dog gets the trick wrong?
You got it. The less prediction error, the better the algorithm is at taking what it's learned and applying it to new situations, new examples it hasn't seen before.
Makes sense. And there are two main types of supervised learning, right? Classification and regression.
Yep. Classification is about sorting things into categories. Think of like a spam filter. It has to decide if an email is spam or not spam. That's classic classification.
Okay, so putting things in the right buckets. And then regression is about predicting a specific number.
Exactly. More of a continuous scale. Think about trying to predict how much a house will sell for based on things like its size, location, all those features.
Okay, I think those are starting to click.
Right.
But then there's this thing, the no information value. What is that all about?
Think of it like your starting point before you know anything. Like you're flipping a coin. If you have zero info about the coin, your best guess is 50-50 heads or tails.
So it's like the default assumption before the algorithm actually starts learning from the data.
Yeah, you could say that. And then the more info the algorithm gets, the more features it can look at, the more it can refine its predictions.
So more features equals better accuracy generally. But the book also talks about this complexity trade-off. What's that all about?
Well, think of it like baking a cake. A few key ingredients make it delicious, but if you start throwing in everything from the pantry...
That could be a mess.
Exactly. Too many features can make things overly complicated, hard to understand, and you might even end up with something called overfitting.
Overfitting, that doesn't sound good.
It's not. It's like the models memorize the training data instead of actually understanding the underlying patterns. So it does great on the data it already knows, but total bombs on anything new.
Got it. So how do we find that balance? How many features is just right?
That's a key question, and we'll explore it more as we go through the book. But the main thing is to be aware of that trade-off. Don't just throw every feature you can think of at the problem.
Okay, good advice.
Okay.
Now, Chapter 2 jumps into optimal classification. So what makes a classifier optimal?
It's about making the best possible decision with the information you have, minimizing the chances of making a mistake, given the data.
Okay, so the ultimate decision-making machine. And the Bayes classifier is kind of the gold standard, right?
Yeah, it's the theoretical ideal. It takes into account all the available information and makes the most statistically sound decision. It's the benchmark, what we're always trying to get close to.
Okay, I see. The book also talks about posterior probabilities. Can you unpack that for me?
Imagine you're a doctor, right? You're looking at a patient's symptoms, trying to figure out what's wrong. You might say something like, given this patient has a fever, cough, sore throat, there's an 80% chance it's the flu.
That's basically a posterior probability. The probability of something belonging to a certain category, like having the flu, given the evidence you have, the symptoms.
So it's like using the evidence to update our beliefs about what's most likely. Makes sense.
And the Bayes classifier uses these probabilities to make those really accurate classifications.
We're like detectives, gathering clues and trying to solve the mystery of what category something belongs to.
You got it. And then the book brings up the discriminant function and the decision boundary. They sound kind of intimidating.
Yeah, a little bit.
Don't worry. Think of the discriminant function like a scoring system. Each category gets a score based on its features. And then the function assigns a data point to the category with the highest score.
So it's like a competition, and the discriminant function is the judge. Exactly. And the decision boundary is like the line that separates the winners from the losers.
Like drawing a line on a map to divide territories.
Yep. Anything on one side of the line belongs to one category. Anything on the other side to the other category.
Okay, I can visualize that.
Yeah.
Now, the book also mentions that sometimes transforming the features can make classification easier. How does that work?
Sometimes the data is just kind of jumbled up in its original form, you know? But if you transform the features, maybe combine them in different ways or look at them from a different angle, things might become clearer.
So it's like rearranging the puzzle pieces until they fit together better.
Yeah, that's a good way to put it.
Okay, so we've got this idea of an ideal classifier, the Bayes classifier, that we're trying to get close to. But I'm curious, even with the best classifier, is there a limit to how accurate we can be?
That's where the Bayes error comes in. It's like the ultimate accuracy ceiling.
So no matter how good our classifier gets, we can never do better than that.
Right. It's determined by how much overlap there is between the categories. If they're totally distinct, the Bayes error would be 0. But in real life, there's almost always some overlap.
So we can strive for perfection, but we have to accept that there's always a chance of making a mistake.
Exactly. It's about managing expectations and understanding the inherent limitations.
Okay, I think I'm starting to see the bigger picture. We've got this ideal, this benchmark, and we use all these techniques to try and approach it, knowing there's a limit we can't quite break through.
That's a great summary.
All right, feeling more confident now. Now, Chapter 3 takes us to sample-based classification. What's the key difference here?
Up until now, we've been assuming we know everything about the data, the probability distributions and all that. But in real life,
We rarely have all the information.
right. So sample-based classification is all about working with limited data, making the best of what we have.
It's like trying to solve a puzzle with only a few pieces.
Exactly. And that means we need to be extra careful about overfitting, making sure our model can generalize well to new data.
Okay, and the book talks about different types of errors that can come up here. Can you break those down for me?
Sure. So remember that Bayes error, our theoretical limit? Well, in the real world, we have to estimate the error based on our sample data. So there's conditional error, which tells us how well the classifier is doing on this specific sample we have. And then there's expected error, which takes into account that different samples can be a bit different.
So conditional error is like a snapshot of how we're doing right now, and expected error is more of a long-term average.
Exactly. And the big idea here is consistency. As we get more and more data, does our classifier get closer and closer to that optimal Bayes error?
So consistency means our classifier is reliable in the long run.
You got it.
This is where my intuition sometimes gets me in trouble. I figure if my classifier does well on the data I have, it's all good, right?
But that's where overfitting can sneak in. It's like memorizing answers for a test without really understanding the material.
So we need to make sure our model isn't just memorizing the data, but actually learning the underlying pattern.
Exactly. That's why a large and representative sample is so important. It's like polling people. If you only ask people in one neighborhood, you won't get an accurate picture of what the whole city thinks.
Okay, so a diverse data set is key. And we'll dig more into how to avoid overfitting later, I'm sure.
Definitely.
All right, Chapter 4, parametric classification. So what does that mean, parametric?
It's like we're assuming a certain shape for the model, a certain structure. We're saying, we think the data follows this pattern, so we're going to use this type of equation to represent it.
So we're adding some constraints to make things more manageable.
Yeah, you could say that. It can make learning more efficient, but of course there's always the risk.
Yet our assumptions are wrong.
Exactly. So
Well-
we need to understand the assumptions behind each method and choose wisely.
Okay, makes sense. Let's look at some of these specific methods. The book starts with the nearest mean classifier. Sounds pretty intuitive.
It is. Think about sorting marbles by color. You could find the average color of each group and then assign new marbles to the group whose average color is closest.
So find the center point of each group and see which center a new data point is closest to.
That's the idea.
Okay, got it. Then there's linear discriminant analysis, or LDA. That sounds more complex.
It's a bit fancier, yeah. Imagine you have a scatter plot of data points from different categories. LDA tries to find the best line, or in higher dimensions, a hyperplane, that separates those categories as cleanly as possible.
like drawing a line in the sand between the two groups.
Perfect analogy.
But what if the categories aren't so neatly separated? What if we need more than just a straight line?
That's where quadratic discriminant analysis comes in, or QDA. It allows for more complex, curved boundaries.
So we're getting fancier. But more flexibility can also mean
More complexity. QDA can be more computationally expensive and might overfit more easily if we don't have enough data.
So again, it's all about finding that balance.
Exactly.
Okay, we've got NMC, LDA, QDA. Anything else we need to know about parametric classification before we move on?
Oh, one more important thing. Regularization. Remember how we talked about overfitting?
Where the model gets too cozy with the training data and doesn't generalize well.
Right. Well, regularization helps prevent that by adding a penalty to complexity.
So it's like a cost for being too clever.
Kind of. It encourages the model to find a simpler solution, which is usually better at generalizing. Think of trying to fit a curve to some data points. A simple curve is more likely to capture the real pattern than one that's all wiggly and overfit to every single point.
Okay, I see. So regularization is like adding some smoothing to prevent things from getting too jagged.
Exactly.
Now on to Chapter 5, non-parametric classification. How is that different?
In parametric classification, we made assumptions about the shape of the model. Non-parametric methods are more flexible. They don't make those strong assumptions.
So more adaptable.
Exactly. They let the data speak for itself, you could say.
I like that. What are some of the popular non-parametric techniques?
One of the simplest is k-nearest neighbors, or KNN. Imagine you're trying to classify a new data point. You look at its k closest neighbors in terms of their features. Those are the data points that are most similar to it, and assign it to the category that appears most often among those neighbors.
So it's like asking your neighbors for their opinion and going with the majority vote.
That's a great way to put it.
Okay, makes sense. What are the pros and cons of KNN?
Well, it's easy to understand and implement. It can handle complex boundaries without those strong assumptions, but it can be computationally expensive for large data sets.
Right, I can see how comparing everything to everything else could get slow.
Exactly. Another useful technique is kernel density estimation.
Kernel density estimation. Okay, remind me what that's about.
Remember how we talked about probability distributions? It's a way to estimate the probability density at any point, even if we don't have a specific formula for the distribution.
I need a visual for this one.
Imagine you're dropping grains of sand on a table. The density of the sand at any point represents the probability density at that point. Kernel density estimation is like smoothing out that sand pile to get a continuous estimate across the whole table.
Ah, okay. So instead of having separate piles of sand, we're making this smooth landscape of probabilities.
Exactly.
All right, and the book also mentions this cover-Hart theorem. What's that all about?
That's a cool theoretical result. It says that even with a really flexible approach like KNN, there's still a limit to how well we can do. The error rate is always going to be at least a certain amount no matter what the data distribution is.
So even with all our cleverness, there's still a fundamental limit.
It's a good reminder to stay humble.
Okay, we've explored parametric and non-parametric classification. Feeling pretty good about those. What's next?
Well, Chapter 6 brings us to function approximation classification.
Function approximation. Sounds like we're getting into the heavy math now.
We are. But the idea is still pretty straightforward. Instead of assigning data points to categories directly, we're trying to find a function that maps the input features to the output class label, like drawing a curve that separates the categories.
Okay, so instead of discrete categories, we're looking at more continuous functions.
Exactly.
Can you give me a real-world example of where this might be useful?
Sure, like trying to predict if a customer will click on an ad based on their browsing history and all that. We could build a function that takes all that information as input and then outputs a score, like a number between 0 and 1, representing how likely they are to click.
So it's like creating a personalized prediction machine.
Exactly.
And the function could be all sorts of things, linear, nonlinear, even those neural networks we hear so much about.
Yep. It depends on the complexity of the problem and how much data you have.
All right, I see. And the book mentions support vector machines, or SVMs, as a powerful example of this approach. What's so special about SVMs?
SVMs are like master swordsmen, finding the most elegant and efficient way to separate the categories. They find that line, that hyperplane, but they try to maximize the distance between the categories and that line.
So it's not just about finding a line, it's about finding the best line, the one with the most breathing room.
Exactly. It makes the classifier more robust. And they have another trick up their sleeve: kernels.
Kernels. Okay, what are those?
Think of it like this. Sometimes the data is just too tangled up in its original form to find a good separating line. Kernels are like mathematical functions that can untangle the data, transform it into a higher dimensional space where it's easier to separate.
Okay, my brain is starting to hurt trying to picture that. But The takeaway is kernels give SVMs even more power.
Exactly. They've been really successful in all sorts of classification problems.
All right, now I'm sensing another big topic coming up. Neural networks. They're like the rock stars of machine learning. What's all the hype about?
Neural networks are fascinating. They're inspired by how our brains work, all those interconnected neurons.
Oh, it's like building a mini brain inside the computer.
In a very simplified way, yes. And just like our brains learn from experience, neural networks can learn from data.
Okay, but there are so many different types of neural networks. It gets overwhelming.
You're right. But at their core, they all share the same building blocks. Neurons, layers, connections. The different types are just variations on this theme.
All right, let's try and demystify some of those variations. The book talks about multi-layer perceptrons, or MLPs. What are those all about?
MLPs are like the basic blueprint. They have an input layer where the data comes in, one or more hidden layers where the learning happens, and then an output layer where the results come out.
So the hidden layers are where the magic happens.
You could say that.
Okay, what about those convolutional neural networks, or CNNs? They're all over the place in image recognition.
CNNs are specifically designed for images. They use these things called convolutional filters. Imagine sliding a magnifying glass over the image to pick out features from different parts of the image.
So they're like visual experts, breaking down the image and understanding it piece by piece.
Exactly. And they've been incredibly successful in things like image classification, object detection, even generating new images.
Okay, and then there are those recurrent neural networks, or RNNs. Those seem to be taking over natural language processing.
RNNs are great at handling sequences like text or speech. They have this special ability to remember past information and use it to understand the current input. It's like reading a sentence word by word, and RNN remembers the previous words to understand the current one.
So RNNs are like storytellers, weaving together a narrative.
You got it. And they've been amazing for machine translation, speech recognition, even generating text.
Wow, neural networks really are everywhere.
Oh.
But with all this power comes responsibility, right? The book mentions some challenges.
Absolutely. They can be complex, need a lot of data and computing power to train properly, and they can be black boxes, meaning it's hard to understand why they make the decisions they do.
So it's not just about making bigger and more complex networks. It's about understanding them, using them responsibly.
Exactly. That's something we'll keep coming back to.
All right, great. That was a whirlwind tour of neural networks. Feeling a bit more confident about those now. Chapter 7 takes us to error estimation for classification. Why is that so important?
Well, you can train your classifier, and it might do great on the training data, but how do you know how well it will do on new data it's never seen before?
Right. It's like acing a practice test, but then freezing up on the real exam.
Exactly. Error estimation is about trying to predict how well our classifier will do in the real world.
Like giving it a trial run.
Yeah, you could say that.
Okay, so what are some of the techniques for doing that?
One of the most common is the test set approach. We split our data into two sets, one for training the classifier and one for testing it data it hasn't seen before.
So the test set is like a mock exam. We see how the classifier performs under pressure.
Exactly. And the error rate on that test set gives us an idea of how well it might do in the real world.
Okay, that seems pretty straightforward. But there are other techniques too, right?
Yeah. There's resubstitution estimation, where you use the same data to train and test the classifier.
Wait, isn't that a bit like letting the student grade their own homework?
You got it. It's overly optimistic. It tends to underestimate the true error rate.
So not very accurate. What are some more reliable options?
Cross-validation is a good one.
How does that work?
Imagine you're making a dish for a potluck. You want feedback, right? You could ask one friend, but their opinion might be biased. It's better to ask several friends and average their opinions for a more representative assessment.
So cross-validation is like getting multiple opinions to reduce the risk of bias.
Precisely. We split the data into multiple parts, use each part as a test set, and then average the results.
Okay, that makes sense. And what about bootstrap estimation?
Bootstrap is interesting. It's like taking multiple snapshots of the data, each one slightly different, and training a classifier on each snapshot. Then we combine those results.
So multiple perspectives on the same data.
Yeah, you could say that.
All right, that's a lot of options. Seems like choosing the right technique depends on the data and the problem.
Absolutely. The book gives some guidance on that, but there's no one-size-fits-all solution.
Okay, good to know. Now, Chapter 8 is all about model selection for classification. How do we choose the best classifier for a particular problem? It's like being at a buffet with endless choices. How do you pick the perfect combination of dishes?
Great analogy. It's easy to get overwhelmed. Model selection is all about balancing how well the model fits the training data with how well it avoids overfitting.
Right, we need a model that's both accurate and generalizable.
Exactly. The book talks about the bias-variance trade-off, which is a key concept here.
Okay, break that down for me.
Imagine you're throwing darts